All right, let's take a look at our worksheet from Newton's second law that we were working on since Monday here. We had requests for 5 questions, 11, 12, 14, 15, 16. We'll do number 11 right now. It says, a car is pulled with a force of 10,000 newtons. The car's mass is 1,267 kilograms, but the car covers 394.6 meters in 15 seconds. So we apply a force, we have a certain mass, and so we're given a displacement and a time. Now, if you calculate the acceleration of the car, there's 2 different ways we can do it. One's using the force and the mass. One's using the displacement and the time. But we get a different answer in both cases. So what's going on in this question? What's going on here? Well, we're saying that theoretically, if we've got a force and a mass, we should get a certain acceleration. But realistically, we're not getting that acceleration. Realistically, it doesn't move as far as it would if we did get that acceleration. So there's something causing it to not accelerate as quickly as it theoretically should. We'll deal with that when we get to question D, the force that caused the difference in acceleration. Let's look right now at question A, number 11. That says, what is the expected acceleration of the car from the 10,000 Newton force? This is what we should get. This is what we think we're going to get based on the force and the mass. So we're going to say here, for that part of it, we're going to say the force is 10,000 newtons. And we're going to say the mass here is 1,267 kilograms. Let's get the acceleration that way. When we do, we're going to say A is equal to F over M, right? This is Newton's second law. Okay, Newton's first law, if you remember that from last week, said an object at rest stays at rest, an object in motion stays in motion, straight line, constant speed, until acted upon by an unbalanced force. In other words, Newton's first law, the law of inertia, was kind of like the law of keep doing what it's doing. Right? Keep staying at rest if it's at rest, keep moving if it's moving. The law of keep doing what it's doing. Whereas the second law is the law of the exact opposite. The law of not keep doing what it's doing. It's the law of let's accelerate. Okay, and we learned on Monday that there's 2 things that cause an acceleration. One's a force. Bigger the force, the bigger the acceleration. The other is mass. Mass affects acceleration inversely. So as bigger the mass, you get the smaller the acceleration. So the first law, keep doing what it's doing. Second law, we're going to accelerate in the second law. The exact opposite of keep doing what it's doing. This is Newton's second law. A is equal to F over M. We're going to say the force is 10,000 newtons here. And we're going to divide that by the mass of 1,267 kilograms. And it seems to me we got 8 or 9, something like that. When we calculated that value, what did it work out to be? 7.89 meters per second. Can you give me some more decimal places there? Anybody have more? 7.892659 meters per second squared. Now, if you go back to our original data, and we have to determine how many sig figs an answer should be, we're paying especially close attention to sig figs now, right? On our next test, it counts. Didn't on the last one. Next test, it does count. Go back to our data. This says 5 digits. This says 4 digits. The other data in the question has 4 digits and 2 digits. We're going to round this to 4 digits. When you look at the question, you see 15 seconds is only 2 digits. Why am I not rounding my answer to 2 digits? Because I didn't use the time. If I used the 2-digit time, then I'd have to round it to 2 digits. If we didn't use it, then who cares? So only use this data. Let's use 4 significant figures there. B says, what's the actual acceleration? Well, we're given here that VI is equal to 0 meters per second. We established that on Monday here. The displacement here is 394.6 meters, and the time interval here is 15 seconds. So again, theoretically, we should get the same value, but we're not going to, and you're going to see that in just a moment here. I want to find A. Let's probably go D is equal to VIT plus 1/2 AT squared. Notice how we're using an equation from our last unit. We're not abandoning any of that stuff, right? We're allowed to still use those. F equals ma, Newton's second law, is just another group B equation. It goes in with the other 5 that we learned in the last unit. Now, most times we're going to use F is equal to m times a here, but sometimes we're still going to have to use one of the other ones in conjunction with it. This is 0, solving for a. Let's say delta D divided by 1/2 t squared, because they're multiplied by a, equal to a. I get 394.6 divided by 1/2 of 15 squared. And what do we get for that one? 3.507, thank you, Nick, meters per second squared, which this time we're going to actually round this, Nick, to 2 digits, right? 0 doesn't count for significant figures. This is 4 digits. This is 2 digits. Final answer should be 2 digits, 3.5 meters per second squared. So we expected 7.8 from our force and our force and our mass, but we actually got 3.5, as shown by our data here for displacement and time. See, what's the difference in accelerations? Well, we just subtract, right? Works out to be 4.393. D. What force caused that difference in accelerations? Why did it accelerate at a rate less than half of what I expected? Able to give me an idea there, Hugh? It could be air resistance. There would be some air resistance for sure. What's likely to be a bit of a bigger factor, though? Friction. We don't really know for sure if air resistance is not as big as friction, but friction is usually bigger if it's on the ground. So we're going to say friction, but hey, you put air resistance, this is a test question, and you put air resistance in there, I couldn't mark that wrong because we don't know for sure, right? In a sense, air resistance is a type of friction anyways because it's air rubbing against it as opposed to the ground rubbing against it. And finally, question E says, what's the magnitude of the direction of the force that causes the difference in the acceleration? In other words, how big is the friction force here? Well, if we have the acceleration caused by friction right here, and we want to find the force, let's just say it's m times a. M is 1267, and a is 4.393. What does that work out to be? 5,565.931 newtons, which we're going to round out actually to 5.6 times 10 to the 3 newtons. Now, sometimes you look at this and say, hey, that was 4 digits. This is 4 digits. Final answer should be 4 digits. No, because ultimately we had to use time to get that. Although we did it a couple of questions earlier, that time still affected this value. So my final answer still needs to be 2 digits. About number 12 now. It says a little car has a maximum acceleration of 2.57. What's the new maximum acceleration if the little car tows another car that has the same mass? Interesting. Interesting question there. We don't know what the mass is. All we know is that we got 2 of them now. What's the new maximum acceleration? Well, we know that acceleration is force over mass. If the acceleration was 2.57, without knowing what the force is, without knowing what the mass is, but now we have two times the mass, twice the mass of what we had before. Anybody want to take a stab at what the acceleration would become here? Yeah, it's half. Good. So 1.285 meters per second squared. Let's logically think about that. Mass increases, acceleration decreases. Mass doubles, acceleration goes down by a factor of 2. Gets cut in half. Okay? Acceleration is inversely related to the mass. 14 is our next one that we need to do. Similar question here, actually. A cartoon plane with 4 engines can accelerate at 8.9 meters per second squared when one engine is running. What's the acceleration of the plane if all 4 engines are running and each produces the same force? Once again, A is equal to F over M. One engine can accelerate at 8.9 meters per second squared. If we've got 4 of them, each one applies the same force. In other words, if force goes up by a factor of 4, it's 4 times what it was, then what happens to the acceleration? It goes up by a factor of 4. So it becomes, what do we have here? 8.9 meters per second squared. We're going to say 8.9 meters per second squared times 4, which gives me 30, what is that, 37.6? 35.6? Oh, yeah. You're right, 35.6 meters per second squared, which we should actually round that to 2 digits, or 36 meters per second squared. Is that okay? You don't have to do any math on that one, really, other than just a little bit of reasoning in your mind. 15. What do we got for this one? Fifteen says, another similar question actually, but maybe a little bit harder. While dragging a crate, a workman exerts a force of 628 newtons. Later, the mass of the crate is increased by a factor of 3.8. If the workman exerts the same force, how does the new acceleration compare to the old acceleration? Same type of thing here, right? A is equal to F over M. If the mass increases by a factor of 3.8, does that increase or decrease the acceleration? Mass goes up, acceleration goes down. So if you increase the mass by 3.8, then the acceleration will decrease by a factor of 3.8. So all we're going to do here is say 628 newtons. No, we don't even have the acceleration. All we're going to say is the new acceleration is whatever the old acceleration was, the original acceleration divided by 3.8, because it goes down by a factor of 3.8. If mass goes up, acceleration goes down. A similar type question. So it looks like, or those are the type of questions we're having trouble with, right? Is those don't really have a number to calculate with, just going to have to reason a little bit there. 16 says a rocket accelerates in space at a rate of 1 g. And on the front of this sheet, I told you that 1 g, g is the acceleration divided by 9.81. So 1 g would give us an acceleration of 9.81 meters per second squared, just not necessarily downwards. The rocket exerts a force of 12,482 newtons. This one's a little bit different, actually, Laura. Later on, this is my original force. My new force later on, we'll call it F2, is 46,458 newtons. What's the new acceleration? Let's do this. Let's say A is equal to F over M. A1 is F1 over M. Let's say mass is equal to F over A. So it's 12,482 newtons divided by 9.81. What do we get for that? 1,272.4 kilograms. All right, so there's the mass, thank you. There's the mass of this rocket, 1,272.4 kilograms. The mass of this rocket isn't changing, but now we're applying a bigger force. We want to find the acceleration. The force is now 46,458 newtons, but the mass is still the mass. The mass is still 1,272.4 kilograms. And what do we get for the acceleration for that one, Grace? 36.51 meters per second squared. We're going to round that to, looks like 3 digits there, or 36.5 meters per second squared. Now, you should expect a higher acceleration, right? We made our force bigger. Bigger forces mean bigger acceleration. How would you figure out the number of G's, though? Yep. Right. So 36, let's use the unrounded number there, 36.51 divided by 9.81. What is that going to give me? About almost 4? 3.72? And it would be 3 digits there, 3.72 G's. That's one of the things that you're going to have to do fairly often on your West Edmonton Mall amusement park assignment come May, is calculate the number of G's. And I know I'm going to get from people, oh, how do you calculate G's? Well, there's 2 ways to do it. You've just learned the first way. Okay, the first way is take the acceleration, divide it by 9.81. Done. If you have an acceleration, divide it by 9.81, it gives you the number of G's. How heavy you feel compared to how heavy you actually are. So we spent the last couple of days talking about forces. We know a force is a push or a pull. We know the effects of a force. It either accelerates the object or deforms the object. We know how to calculate force, including, as we talk about Newton's second law, acceleration, mass, and so on. Today we're going to talk a little bit about some types of forces, some of the things that can give us forces, some of the things that can push or pull on an object. There's 3 specifically that we're going to talk about today. First one is weight. Now I want to distinguish weight with another term that most of you will get mixed up with weight. That is mass. Okay, mass and weight are 2 different things. Mass is the amount of matter that's possessed by something. That's the same no matter where you go in the universe. On Earth, I have a mass of 70 kilograms. On the moon, I would have a mass of 70 kilograms. In outer space, I would have a mass of 70 kilograms. My mass is the amount of matter that I possess, and it's the same anywhere I go in the universe. My weight, on the other hand, changes. It not only changes if I go to the moon or somewhere else in the universe, it can even change from location to location on Earth. Weight is the force of gravity that acts on an object. And because the acceleration due to gravity is different everywhere on Earth, we always say it's 9.81, right? But that's not quite true. It varies. In Calgary, it's probably more like 9.80. In Vancouver, it would be more like 9.82. The closer you are to the center of the Earth, in other words, really the closer you are to sea level, then the stronger gravity is going to be. It averages out to be about 9.81. But it varies a little bit. Go to the top of Mount Everest, it's 9.7 something. You're going to weigh less at the top of Mount Everest because gravity is less, but your mass will be the same. The force of gravity acting on the object is the weight, and it's calculated by multiplying m times g. Now, g is just the acceleration due to gravity. Now, that acceleration due to gravity, we're going to put in quotation marks here, is 9.81 meters per second squared. It's in quotation marks because it's not necessarily that value. That's just the value that we think of it as, because that's the one that we're used to using. On the moon, G would be about 1.6. In Vancouver, it might be 9.82. On Earth, we'll assume 9.81 no matter where we are, unless we're told different. Just understand that it can be a little bit different. Mass, weight, normal force. Okay? Weight is related to mass. We get them confused sometimes. Normal force is related to weight. We get them confused sometimes. The normal force is the force of the ground, although I'm going to put ground in quotation marks because it's not always the ground. The force of the ground acting up. I'm going to put that in quotation marks as well. acting up on an object at 90 degrees. We put the word up in quotation marks as well because it doesn't always act up. We think of it as the ground and we think of it as acting up, upwards, but the reality is it could be, right now it's your seat. Your seat is pushing up on you. That's not the ground. Now the normal force on your seat is the ground. The normal force on you, on your bum, is your seat pushing up. It doesn't always have to push up either though. Sometimes it pushes at an angle. We think of it as being up. For instance, here's your desk on the ground, or a box on the ground, let's say. Gravity acts down on that box. Newton's first law says that box is going to accelerate unless there's no net force. An object at rest, if it stays at rest, must have no unbalanced force acting on it. The forces must balance. Well, if gravity acts down, something's got to act up. That's the normal force that acts up. And it's straight up. Force applied by the ground straight up on this object. But if, on the other hand, that box is on a hill like this, gravity acts down. But the normal force actually acts like this. Notice the angle of the normal force with the ground is 90 degrees there. Notice the angle with the normal force and the ground is 90 degrees right there. So we say that it's the force of the ground pushing up, although it could be the force of your chair pushing up. We say that it's acting up, but really it could be up at an angle. It's always at 90 degrees though. Always at 90 degrees to the surface. Here's another one. You guys are going to go on a field trip in about 2 months to study the physics of amusement park rides at West Edmonton Mall. And as part of that, you guys are going to ride in a roller coaster upside down. Unless you open your eyes or look sideways, you will have no concept that you're moving upside down. If you look forward, it's going to look like there's a hill in front of you. The track is curving upwards away from you. You're going to feel like you're going uphill, but really you're upside down. Unless you look sideways and you can see everything in the amusement park upside down, then you're not going to know that you're upside down. There's a force of gravity acting on you downwards. But there's also a normal force acting on you. It's the force of the track acting downwards. It's not the force of the ground, it's the force of the track. It's not the force acting up, it's actually the force acting down. But it is acting at 90 degrees. The normal force is always at 90 degrees to whatever it is that's causing it. Does that make sense? We'll talk a lot more about that as the year goes on. One more little thing with normal force here. The normal force is the apparent weight What does that mean? The apparent weight of an object. The apparent weight of an object. Yes, still with normal force. The apparent weight of an object is how heavy the object feels. What causes your weight? It's gravity. But you know what? You don't feel that. You don't feel your weight. You think you do, but you don't. You feel the normal force. You feel the apparent weight. You're sitting in your desk right now. Wait, I feel gravity pulling down on me, right? I'm standing on the floor. I feel gravity pulling down. You're sitting in your desk. You feel gravity pulling down, right? Wrong. You don't. You do not feel gravity pulling down on you. What do you feel? You feel the desk pushing up on you. What do I feel right now? I feel the floor pushing up on my feet. Now, normally, that force of the floor or the force of the desk is the same value as the force of gravity. So whatever I really weigh is how heavy I feel like I weigh. Normal force, gravity, same value. I feel as heavy as I really am. But there are some cases where the normal force is bigger or smaller than the force of gravity. So I feel heavier or lighter than I really am. Can you give me a situation in which I might feel heavier than I really am? Not going to another planet that has stronger gravity or something like that, right? On Earth, when can I feel heavier than I really am? Perfect. Perfect example. When you're in an elevator, and not always in an elevator, right? When you're in that elevator, going up, maybe you're in an elevator of a really, really, really tall building. So it's an elevator that moves really fast. Okay, better yet, it's an elevator that accelerates really quickly. It doesn't matter how fast it moves, it matters how fast it accelerates. You get in that elevator, and it accelerates upward at a really high rate. You ever feel yourself being pushed against the floor there? You feel really heavy there. That's because in order to go upwards, the floor has to push up on you harder than gravity pulls down on you. Otherwise, you wouldn't go up. If the floor only pushed up as hard as gravity pulled down, you'd stay where you are. Floor pushes up harder than gravity, you feel heavier than you really are. When do you feel lighter than you really are? Yep. When it accelerates downward. You're at the top of the CN Tower, and the elevator falls out from underneath you almost, right? You feel lighter. Why? Well, because in that case, if it accelerates downward, gravity has to be bigger than the normal force. It's the opposite, right? If gravity is bigger than the normal force, you feel lighter than you really are. Give me a situation in which you would feel weightless. You're not. Okay? On Earth, you're never weightless. You always have weight. But give me a situation in which you would feel weightless. Yes, good. When you're falling, when you're free falling. If you're in that elevator and somebody cuts the cable or it breaks, and there's braking systems, so you wouldn't plunge to your death, but let's pretend for a second that you would just free fall downwards. You would float around in the elevator. Wouldn't that be cool for a short time? Yeah, you got to the ground. That whole thing, by the way, about the elevator cable snapping and you jumping just before you hit the ground doesn't work. Doesn't work. Don't try that. Okay? You still die. It would just be about a third of a second later. That's all. You just prolong your life by about a third of a second. That's all. As you free fall downward, there is no floor pushing up on you. And if there's no floor pushing up on you, you feel weightless. NASA has a jet that they use for training astronauts. There's all kinds of things they do to train astronauts, but one of the things is they use this jet, they call it the Vomit Comet. They take this airplane up to the edge of space, as high as they can possibly go, and still run the engines by combustion. And then they kind of cut the engines, and then they dive bomb towards the ocean. It gives, and they do that for about a minute at a time, and that gives the people inside this airplane the opportunity to experience no normal force. They still have weight. Gravity still acts on them the same way as it does on you and I. They don't weigh any less. But because there's no normal force acting on them, no floor acting on them, what do? They float around for a minute in this airplane. They call it the Vomit Comet, by the way, because the first couple of times you do it, usually you puke, you vomit. Okay, but in the end, once you get used to it, you realize what it's like in space with no gravity. You feel weightless. Make sense? Talking about space for a second. Here's the Earth. Here's the space station orbiting around the Earth. Space station wants to go this way. Wants to go in a straight line, right? Everything wants to go in a straight line. It's traveling at 30,000 kilometers per hour, about. And it wants to go off in a straight line at 30,000 kilometers per hour, but it doesn't. So you must have an unbalanced force acting on it. You do. It's this way. It's gravity pulling it in. But it doesn't go straight down. It doesn't fall straight down because it's got inertia taking it off in a straight line. So really what it does is goes in between, right? Okay, gravity wants to pull it down. Its inertia wants to take it out that way. So it ends up going in between. Well, now gravity's acting this way. Now it's going down here, and so on, and so on, and so on. Ends up going in a circle around the Earth. But there is only one force acting on it this whole time. It's gravity. When only one force acts on something, it free falls. The space station is free falling constantly. Constantly. If you're in the space station, you're not weightless. If you're in the space station, gravity is almost as much as it is here, maybe 9.2, 9.3 meters per second squared. You weigh almost as much as you do here, but you float around because you're free falling. It's like you're in the Vomit Comet, but not for a minute. It's like you're on a free fall ride at an amusement park but not for 3 seconds. Rather, you're there for 6 months. It's like you jump off a building and you fall and you fall and you fall and you fall for 6 months nonstop. It makes you feel like you're weightless and you float around as a result of that. That makes sense? Okay, here's another force. Friction. Friction is a force that acts between two objects or between two surfaces that opposes motion. When you slam on the brakes of your car, there's a force of friction that acts between the wheels of your car, the tires of your car, and the road. That resists motion. That's a good thing in that case because it stops you. Ironically, that's actually how cars move as well, is by friction. A resistive force, a force that resists motion, is actually what propels a car forward. A force that resists motion is actually a force that causes motion. The fact that your wheels don't slip on the road as you put your foot on the gas pedal, that force that is keeping the wheels from spinning, resisting the motion of the wheels relative to the road, is what actually propels you forward. Okay. The force between two surfaces that resists motion. Okay, now, different surfaces have different amounts of friction. You slam your tires, slam your brakes on pavement, and there's quite a lot of friction. You'll slow down, you'll stop pretty quickly. Slam your brakes on ice, what happens? You keep going in a straight line. Because Newton's first law says if there's no unbalanced force, and there isn't very much friction there, okay, very low friction on ice, then you're going to keep going in a straight line at a constant speed. There's two kinds of friction. The first kind is called static friction. It's the force of friction that keeps an object from beginning to move. Okay, push on Adam's desk right now. Pushing to the right on his desk doesn't move. Well, something must be countering that. That's static friction that's countering my applied force. Push on it harder, static friction pushes back harder to oppose that motion. But if I get his desk moving, all of a sudden, it's not static friction anymore. That's what we call kinetic friction, or dynamic friction. Static friction keeps an object from beginning to move, or at least tries to. Kinetic or dynamic friction resists motion that is, or resists an object's motion if it's already moving. We'll talk a lot more about those two kinds of friction tomorrow, including some calculations. Finally, this last term here, last one we're going to do today, in fact, free body diagram. It's not a force. It's not a type of force. A free body diagram is just that. It's a diagram. It's a diagram that shows all the forces acting on an object. On your desk right now, there are two forces. Okay, there's your desk or a table or something. There's two forces acting on it. There's gravity acting down, and unless your desk accelerates downward, there's got to be normal force acting up. When I push on Adam's desk, there's a force to the right that I'm going to call the applied force. If there's only the applied force, what happens to your desk, Adam? It's going to move. It's going to accelerate to the right. If it doesn't move, then it must mean there must have been a force acting to the left that we'll call FF, the force of friction. forces balance, desk doesn't move. If one of those forces becomes bigger so that it's not a balanced forces anymore, then all of a sudden your desk starts moving. If the normal force can't provide as big of a force because maybe you're on ice and the ice breaks, then what happens? Normal force is smaller and you accelerate downward because gravity is bigger. Okay, I've got one quick sample for you to do here. We'll ask you to draw this free body diagram at your desk from this example. Then we'll do that one as a class, and then we're done for the day, okay? Okay, let's give it a whirl here. I've got a 20 kilogram object on the floor. We don't have to label, by the way, the 20 kilograms technically to make it a free body diagram, because free body diagrams show forces, not masses. But we might as well label it, because at some point when we're solving problems, we got to write down our givens anyways. Might as well just do it as part of the diagram. We've got a force of gravity acting down. How many people drew the normal force like this? How many people drew it like this? Okay, good, you're correct. How many people drew the normal force like this? Anybody? If you did, you'd be correct. It doesn't matter where we draw the force, whether it's there or the first position, as long as we have it drawn about the same length as gravity because it's the same value, then that's good enough. All right, we got an applied force of 30 newtons. We'll call that FA, or you can call it whatever you want, really. Just label it as 30 newtons. It's acting to the right. Actually, it doesn't say it's to the right. It could be to the left. Bottom line is, though, if it's acting to the right, friction must act to the left. And it's smaller, so we want to make sure that we have that line drawn shorter. Now, you could have drawn it like this, with the applied force to the right and friction to the left right here. Would that have worked? Sure. It doesn't matter where we draw the forces, as long as we have the applied force drawn roughly 3 times as long as the force of friction. Is that okay? These forces don't balance. What's going to happen to this object as a result of these forces? Going to move up or down? No. Going to move left or right? Which way is it going to move? It's going to move to the right because the applied force is bigger. Make sense? Okay, done for the day, guys.